Welcome everyone to our day 3 of Online International Faculty Development Program. I would like to introduce Dr. Tirthankar Ghosal, Scientist, National Center for Computational Sciences, Oak Ridge National Laboratory, United States of America. Dr. Tirthankar Ghosal is a scientist at the Advanced AI Methods at Scale group in the National Center for Computational Sciences, Oak Ridge National Laboratory. He is also a faculty advisor at the University of Tennessee Oak Ridge Innovation Institute. At ORNL, he works on natural language processing of scientific text to build foundation model for science, which would cater to specific downstream use case researchers in collaboration with NASA, ADS, and Universe TBD. Dr. Ghosal obtained his doctoral degree from the Institute of Technology, Patna, with a specialization in natural language processing. He did his postdoc from the Institute of Formal and Applied Linguistics at Charles University, Czech Republic. Before joining ORNL, he was the head of research at SciSpace, a Palo Alto-based company, where he led a team of NLP researchers on various problems related to computational processing of scientific articles to counter the scholarly information overload. In community role, Dr. Ghosal was the organizer and area chair of premier NLP AI Squalcomm conferences like INLG, EMPNL, IJCAI, Force 11, NAACL, AACL, ACL, and workshops like SDP, WIESP, Sumdial, Metrics, and shared tasks or generation challenges like Automin, MUP, Deal, Skiver, Focal, etc. In community roles, he is an active promoter of diversity, equality, and inclusion and was associated with the widening NLP initiative as a chair, EQCL as a current board member, and co-chaired the DEI initiative in NLP conferences like ACL, AACL, IJCL, CNLP, and NAACL. Outside work, Dr. Ghosal spent most of his time with his family, especially playing with his 2-year-old daughter. He enjoys reading literature in his native language, traveling places, and cooking Indian dishes. To brief about our today's session, today we are going to learn about scientific NLP, harnessing large language model for literature-based knowledge discovery. We now hand over the session to Dr. Tirthankar Ghosal. Please, sir.
Okay. Thank you for the introduction. It's my pleasure to be speaking with the participants in this faculty development workshop. Special thanks to my junior from North Bengal University, Deepanjan, for inviting me to speak there. I want the session to be a bit interactive. So please feel free to stop me whenever you want to for any question. This particular presentation is aimed towards introducing the audience towards various problems under the umbrella of AI for science or scientific NLP, and at the end we would try to see the kind of research we are doing as part of the AI for science umbrella within Department of Energy at the National Lab, and see that how we are like with this wave of generative AI and large language models, how we are using them for uh, solving big problems, critical problems to humanity. Uh, yeah. I'm audible clearly, right? And the slides are also visible to move forward.
Yes, sir.
Okay, wonderful. Thank you. Uh, yeah, a bit about myself. Although I've been introduced, but still, I am a scientist at the AIMS group in NCCS, Oak Ridge National Lab, also a faculty advisor with the University of Tennessee, Knoxville. I'm a NLP researcher or practitioner by training since 8+ years. I finished my PhD at IIT Patna, postdoc from Charles University, Czech Republic, and did 2 stints of leading to NLP teams at SciSpace and Freddy. And this is a photograph of my city, Siliguri, where I belong, and I did my master's at University of North Bengal. Yeah. To begin with, I would want to introduce the National Center for Computational Sciences, which houses the Frontier is the division where I belong, and the Frontier is currently the fastest computer in the world, and it is the first computer to break the exascale barrier in computation. And we are fortunate and privileged enough to conduct our experiments on Frontier. We have also other leadership class supercomputing systems, including Summit, Titan, Alpine, Andes, which regularly feature within the top 20 supercomputers in the world. And now we are moving to the next era of supercomputing, where our OLCF 6, which is the Oak Ridge Leadership Computing Facility, is geared towards AI-based computation, or what we call as the next generation of machines. So, yeah, what are we going to discuss today? We could discuss the domain of scholarly document processing, which is essentially scientific knowledge discovery through the lens of NLP. Discoveries are made across different domains, be it physics, chemistry, other basic sciences. Here in scientific NLP, we try to see that how can we leverage the power of text encoded in scientific papers, in scientific artifacts, to drive discovery of new knowledge or to solve mission critical problems. We'll also see the influence of LLMs in science and science applications in some examples, and further that we'll move into ORML efforts with LLM and generative AI for different downstream problems under the umbrella of AI for science or AI for scientific knowledge discovery. So let's start with literature-based discovery, or LBD, which was initially proposed in 1980s by Swanson, where the idea was that if we have tons of papers to our disposal, and it's probably impossible for a certain human to read all the papers, even in his or her own domain, right? So, as a scientist, what we do, we read papers, we conceptualize them, we try to extrapolate ideas, we brainstorm, and then we come up with some hypothesis, and then put that hypothesis into experimentation. But all this only happens when we do more and more literature survey, or when we do more and more readings of our relevant literature. But as you can see, with the explosion of the World Wide Web, and also the explosion of scientific enterprise, I would say, there have been so many papers, tons of papers, exponentially increasing the literature base. We are probably are unable to cope up with the rising number of papers that are coming up every day, right? And hence, it's impossible for a certain scientist or a certain human to actually read all of them. it is in a hard narrow domain and do or formulate ideas or be aware of the latest state of the art. Per se. So this special form of literature-based discovery where we would want an AI which is very good at numbers, which is very good at scale, to do that literature search and ingestion, and then help us reach new knowledge or frontiers of scientific knowledge sooner than their human counterparts, and then try to attend critical problems in relation to identifying new knowledge, formulating new hypotheses, or eventually new experimentation. So literature-based discovery has been there since 1980s, but probably it accelerated in the last 5-6 years when there has been an explosion of articles on the World Wide Web and with many forms of science communication coming into the preprint, preprint forward like archive and others. So I wrote an article with my colleagues last year about how we can use your free to read, how we can use artificial intelligence to consume and deliver research, and how are the ways AI is reshaping the consumption and communication of research, modern day research. Okay, so as a scientist or a researcher, how do we do what we do? What is our daily life look like? So we explore, we collaborate, we read, we think, we connect the dots, so the ideas, and then form hypotheses, experiment, and then we repeat them outside, right? So it's kind of a life cycle with too many inputs and too many degrees and too many out degrees, and probably culminating into some confusion or findings, right? But as I mentioned about the problem, it's very, very critical for us to be aware of the current state of the art, and since the current state of the art is rapidly changing, it's somewhat very difficult for us to keep up with the pace. So how do we have AI to assist us in that, in this research activity? Scholarly knowledge. The idea is to gather valuable insights from the sea of scientific manuscripts, and it could be a daunting task. Close to 2.4 billion papers are published annually across different domains. This is not including the preprint or other form of research communications or technical reports or artifacts. So it would probably double. So finding the relevant paper which is most relevant to your research, which is most you'd like to read or advance your knowledge on your particular problem, is almost finding a needle in the haystack. So how do we cut through the clutter? We all know that like any other activity, our research pattern is also to some extent polluted with papers which are not very relevant, which does not advance the scientific knowledge to any extent, and they are just there, and they are not helpful at all. So how do we cut through those clutter and reach the pinnacle which we want to reach in order to understand science? Can AI help in this? Because since it's good at scale, it's good at numbers. How do we leverage or how do we harness the capabilities of modern day AI? Yes, but probably still now in an assistive role, not entirely a full-fledged scientist, but probably more like a research assistant. Let's see how. And here comes the domain or discipline of scholarly document processing. So, scholarly document processing, we usually call it an SDP, mines scholarly artifacts, which could be data sets, papers, metadata. It's all certain downstream tasks. And it's most investigated in the NLP community. Also in the information retrieval and sometimes in various studies in the data science community as well. Several problems shape up the scholarly document processing landscape. Uh, you can see here among these you are probably already familiar with. I would discuss the most popular of them, but there are many SDP problems, but these are the most popular probably. Scientific document summarization. So the idea is to uh, generate section-wise long document summaries from scientific articles. Why would we do that? The reason why we would do that is again to reduce the scholarly information overload. But probably summaries are not a good substitute for papers. But at least if you have 20 papers in your disposal and you are at a decision point that which paper I should read, not always the abstract is enough to decide that. And then to make that decision that whether you would want to read a paper or not, scientific summaries could be very helpful. It could be templated summaries which would follow some different template, which follow some definitive template. Abstractive summaries are the generative summaries where the algorithm would, the underlying AI algorithm would generate a summary in its own, it will generate a summary, it does not just extract. The other kind of summary is the extractive summaries where the underlying AI algorithm would extract certain sections or certain sentences from the article to produce a summary. Then we have the topical summaries. So if we want to, do multi-document summarization, like suppose we have 10 papers in our hand and we would want to know that what are the literature studied in those 10 papers. So that's a topic, right? So we can generate topical summaries based on the topic we provide. It could be from a single document as well. Slide automatically generating scientific document, scientific slides or PPTs from research articles is one very interesting problem. And to some extent, there have been a lot more here. Good papers published in previous forums. Automatically generating the scientific posters given the scientific paper. Generating TLDR or extreme summaries, like an elevator pitch. That what was the main contribution of the article? Can you generate that 2 or 3 line summary? So here we are discussing the various tasks that comes under scientific document summarization. From the lens of natural language processing and machine learning. Then we have video summaries. Like suppose that there is a research article and you want to create a video out of it. How do you do it? Like converting the text to video, where an AI would probably explain the science inside the paper in layman terms. So this would be very useful for non-expert audience or policymakers or people who would want to consume science very quickly rather than delving into the technical depth. So many forms of summaries, and then there are already ongoing research and very exciting methods proposed in each of these cases. But now with the wave of generative AI, we see exciting research on abstractive, multimodal summaries, generating slides and posters, including the images which are embedded within the research article. One may try Scholarcy, which is already a publicly available tool to generate scientific summaries. I have personally used this, and it was very interesting. Semantic search. So we probably most of us are familiar with Google Scholar. where we, it's the kind of an indexing engine, and via Google Scholar we also search our literature. But the method that for Google Scholar is mostly lexical, um, where we do not take into account the semantics of the text inside the papers. So the semantic scholar is one such AI-powered research tool for scientific literature developed by Allen Institute for Artificial Intelligence, where we search the scientific literature not only with keywords but also with the semantic association of the query word or the query vector with respect to the articles, and it follows the search, retrieve, and rank paradigm. Question answering, like interacting with the paper. How do you enter into a dialogue with the paper so that you can quickly consume the information within the paper? We call it as interacting with the scientific literature. So finding curated and synthesized answers with respect to the query. For example, if there is a paper on a certain AI algorithm, we might want to know quickly that what was the method used, what was the data set used, what was the main contribution of the paper, or how this paper stands against the state of the art. So all of the natural scientific questions that come to us, how interesting it would be that if you would be able to interact with the scientific paper in form of a conversational AI assistant. This is possible. There are tools now with the help of large language models like GPT-4 or Llama 2. There has been tools that are leveraging retrieval augmented generation to do this stuff. But it's also a research problem. Many papers on scientific question answering. We are also interested in scientific question answering, especially long form question answering. And then it was a very interesting observation. In fact, the modern day LLMs that we see, including GPT or Llama 2 or Mistral, we need something called instruction tuning. I will come to that later. But for instruction tuning, we design Q&A dataset so that the LLM can be posed as a chattable assistant, where you can ask questions to the LLM and get answers just like ChatGPT. Scholarly article recommendation, which is a very crucial thing because we are probably not aware of all the articles that we publish, and it's an important task that we get recommended good science articles to the prospective researcher. For example, we can see in Google Scholar there is now a recommendation engine integrated where based on your search pattern or your search behavior, you tend to get similar kind of articles in your feed or in your profile. We call that as collaborative filtering. Recommendations could be content, collaborative, or hybrid, and those can also be a mixture of all these three, and then the relevant articles to you based on your profile or based on your search behavior would be recommended to you. So recommendation would obviously suffer from the old start problem, where if you probably are or an early career researcher who does not have papers, they would probably suffer from a cold start problem because you have nothing in your profile to actually start the recommendation. But in those cases, content-based filtering helps, where the profile of the researcher is built with certain keywords or their interest. So you can find a good semantic recommendation system already in place with Semantic Scholar, where you can search for not only with keywords but also with extended long form sentences to see which are the papers that are related to a given paper or to a given query. Another kind of task is justifying the citations that are inside the body of the paper. Because not all citations are created equal and not all citations behave equally or serve the same purpose, right? Because like some citations are there which are used for comparing or contrasting a work. Some citations are there which extend the previous where we cite that particular article to say that we are extending that previous work, or some citations are there for future work. Some citations are there for motivating the reader towards the problem statement, and some citations are there that are just there as background or maybe using a given work. For example, uh, let's take the landmark transformer paper. Attention is all you need from Google. So that becomes the basis of all these generative AI and large language vision models that we see in recent days, right? But are all those papers extending the work of transformer? No, they are probably citing the transformer paper because they have mentioned transformer in the paper, and because of a passive effect of that, if you are writing something based on giving a history of transformer, you are citing that paper. But the actual transformer paper, we have no role in the present work. So it is just cited as a background. So what I mean to say is that citations have different functions to perform within a scientific paper. And how do we automatically identify the functions of the citation, or how does it help to understand scholarly impact or to comprehend the scholarly discourse is an interesting problem to investigate within energy technique. Like for example, let's take an example. Unlike some citation, we use the method of this, which has been used previously for parsing. So this is an example of citation functionality within a given sentence. There are three categories of citations we can classify. So at some point in time, I did a research while measuring the pervasiveness of research via citation classification. The idea was that how do we know that if a given citation was significant enough? Because most of the citations that we see in the scholarly literature are just there as a background citation. They don't influence the discourse of the current paper mostly. But there are citations which are really very critical. For example, let's talk about I don't know if you've heard about what to bet or love or this static embedding technique, which were the precursor of BERT and ChatGPT transformer category of models. But if you see the deep learning revolution for NLP, it can be attributed to the 2012 paper by Thomas Piccolo on word vectors, like how do we transform a given text into semantic vectors or numbers, right? But post word to vec, there were a flurry of papers which were built on top of word to vec, like doc to vec, paragraph to vec, note to vec, and others, right? So so that means word to vec was a paper which inspired those papers down the line. But again, if you read the word to vec paper, you know that the central hypothesis of word to vec was word co-occurrence, and that means that two words which co-occur together, they probably would have some semantic equivalence or relation. For example, cat, dog, man, woman, king, queen, right? So boy, girl, right? So although those are not synonyms, but they are semantically somewhat relevant because of the various attributes of properties, right? So what I meant to say is that the central hypothesis of the word to vec paper was again derived from the distributional hypothesis, which says words that are similar tend to co-occur together in most. So So if we trace back which work inspired whom, we can find a lineage starting from distribution hypothesis till the representation learning or till the very super huge transformer category large language models that we currently use today. So, but the current approach of measuring research impact is very frequentist. We just go with numbers that how many times someone or some paper has been cited, but we don't look at how they have been cited. And without knowing the how inside the scientific discourse, we can't tell anything about the quality. And then we already know that there has been a malpractice of citations within academia. So identifying the significance of citations is a very good is a very crucial problem to understand the true impact of scientific research. Aging like or citation counts are biased. It suffers from rich yet richer effects and don't support the emergence of novel works. Right. So yeah. So the applications of this could be that can we establish a research lineage? Can we find an alternate measure of research quality and impact? How do we prevent the irrelevant citations and citation malpractice within the academic community? And with the help of significant citations, can we aid faster relevant literature discovery? And finally, the research, the one particular research that I did here was how do we identify that how much a certain research or a facility was pervasive in the community? The next diagram would explain. So suppose B cites A significantly and which is denoted by red color, and C cites B as well as A significantly. So does A to B to C form a research lineage? And suppose D is a path-breaking work, but D doesn't cite A. So can we infer that A found the work in D? So we wanted to study research propagation or idea propagation or pervasiveness of research via the citation via identifying significant citations in a citation network. This was the paper that we worked on, and we did a small experiment on my particular papers and because I worked on knowledge detection, so we wanted to see that how my work is placed in the network, and can I identify the first paper that sent from our group from the different papers that have cited it significantly, and we can with this we show that we can do that. Albeit we didn't try it on a very large network, but still on a small network of papers we were able to find that which work on whom. Then there is citation intent detection, a problem, a LCP problem where we wanted to study that if a certain citation statement is supporting a cited paper, or is it disputing or making a contract or contradicting the statement of a given paper, or it is just mentioning the paper. So three classes: support, refute, or mention. Supporting means that the subsequent research is confirming or is agrees or is consistent with the earlier work, whereas disputing could be that a certain claim that has been made in earlier literature is being refuted by a paper later in the timeline. So can we identify the supporting and disputing statements or contradicting statements automatically from mining the body of scientific literature? There is one particular tool that has been developed on this hypothesis called CITE. They do this. I'm not sure how accurate they are, but for the very well-known papers, it does a pretty good job in identifying which were the supporting and which were the contradicting citations for a given work. We talked about the elevator pitch summaries or the TLDR. So how do we do contributing sentence extraction from the body of scientific literature? Like if there's a given paper, how do we know which were the statements that signifies the contribution made by the current work? That can you extract what was the main contribution, or can you explain the science in this paper in 2 sentences? Or it is also termed as extreme summarization in one of the papers from Allen Institute for Artificial Intelligence, which is extracting elevator pitch summaries from scientific articles on the contributions of the scientific articles via various NLP techniques. We also did a work on that, which was a state of the art model called PSI, which was a bird-based model for extracting contributing sentences of scientific papers. Um, Along this line, I should mention the NEP contribution graph from graph model, which is from CIB Hanover, where they specify the NEP contributions into 12 different informational units, which could be contributions can be in terms of research problem, in terms of approach or experimental setup, further task, experiments, ablation, or baseline. Um, Facility discovery or identifying scientific named entities within articles. So this was a joint project with the Smithsonian Institution, Astrophysics Data System, NASA, and there was a part of the AACL workshop where the science practitioners we came together for facility discovery or identifying scientific areas. For example, let's say the Chandra telescope, which NASA is very critically interested in, that how Chandra telescope has influenced so many scientific discoveries over years, and how you can automatically identify the contribution of Chandra telescope via mining the loads of scientific papers that have or the research that has used the Chandra telescope in and also manufacturing scientific articles. How do you measure the influence or the scientific influence of Chandra telescope in the scientific community? So this was the one particular problem statement, but then we converted into a shared task or a challenge, where the idea was that can you automatically extract the NASA facilities from astrophysics literature? Then late summary and blog, like this was also shared task we formulated in the first CL shared task challenge in the SBP 2020. So the idea here is that can we write layman summaries of scientific articles from the paper itself, or can we go further and generate scientific blog which explains the science in the paper in layman terms for non-expert audience, for policymakers, or people who just don't have time to deal with the technical depth of the science inside the paper. So this is also a very interesting and challenging task, more so with the multimodal content that we have also, especially in basic science like physics, astrophysics, biology, where images are so very important inside the paper. So you can't really create a scientific blog or a scientific summary without using the images. And how do you explain the image, or how do you auto-generate the caption, or how do you generate an expansion of the image in your summary so that people understand what is the content of the image. This has been a very age-old task, keyword extraction. There are many applications like for better indexing, search and retrieval. Extracting the major keyword from scientific articles is an important task to do for discoverability of the scientific articles in the online space. Before moving on to the next portion, do you have any questions? Okay, take it down. we move ahead?
Yes, sir. Can you?
I wanted to stop for a moment to have some questions from the audience. Should we do that now or should we do it at the end?
As you wish, sir.
Okay. So maybe if there are no questions right now, we can wait until the end. So let's move ahead. So large language models for science via scientific publication mining. So this is an old picture. There are many new models that have already come. Like time, like I think this was uh, timeline of models until 2020, or maybe maybe till April 2020. But there are many more that came post that. So element for science and mind scientific publications emphasizes employing information extraction and NLP techniques to mine scholarly information encoded in research papers, building large language models on text from research articles. More or less, the ethics is the same, but now more focused on scientific discovery rather than in general NLP problems that are there that we discussed so far. Some very related efforts are the Galactica large language model from Meta in 2022, BioMed LM from Stanford, Scholar Bird from the Global Lab in Chicago, Maxwell Bird from IIIT Delhi, probably. Dragon, not sure from where it came, but PyBird from Allen Institute for Artificial Intelligence, and more recently, Olmo and others. We'll come to that. So our current research in order to focus on building foundation model for science from text encoded in research articles. Also, we include images because multimodality is so important nowadays. Are there any questions or something on the chat? I am not able to monitor that. Okay, moving on, and we are also part of the Department of Energy Trillion Parameter Consortium, but the idea is to train a trillion parameter model based for science. We are building science applications on top of base LLM models developed at ORL. We are also building instruction following model for scientific question answering on selected domains. The data curation effort is very, very critical because good quality data is the key, and we could refer to the very recent Alpha 2005 papers where they consistently say that bigger is always the better. So in our data curation effort, we are working on automatically generating deep scientific conceptual questions from papers, not the in general WH category for the questions which is probably easier. The reason why we want to generate that because we want to have very deep interactions with scientific articles, and for that we are leveraging the peer reviews. The questions that the peer reviewers ask in peer reviews, and we have trained the model QPeer on paper review peer, so that given a paper we can automatically generate deep scientific conceptual questions from that. We are using retrieval augmented generation to generate probable answers and then employing human evaluation and feedback from domain scientists. Currently, we are working on only two domains, astrophysics and material science, and via this we are devising the gold standard instruction set for fine tuning or alignment of the LLMs that we have developed in-house. We are generating deep samples, as I mentioned, the rewrite type questions from open peer review. We are employing LLM to generate questions from paper, full text with that. So this was the QPeer paper that I was talking about, where the idea was that we use the and find these science questions that are asked by reviewers in peer review to automatically generate a similar category questions from a incomplete paper. Once the questions are generated, we are using vegetable automated generation for the answers. So it employs a three-stage approach, where the first stage is question decomposition, followed by query focus statement, query focus statement retrieval and ranking. We are currently using COI Word for that. And then synthesizing the retrieved artifact for generating the answer, which is eventually done by the downstream error. Human evaluation and feedback, a very, very critical component after supervised fine-tuning. We know ChatGPT has been aligned with featural reinforcement learning with human feedback. So the motivation is that if the QAPI makes sense, if they are relevant enough, is the answer that has been generated automatically is correct, and how do we fix the generated answer? That is the domain scientists are working on it, which we call as a feedback loop. So the models that we are currently using, or we have aligned, are Forge, which is developed in-house URL by Juji, who is my colleague, Galactica, the Llama 2 filter modules, and the way we are insertion tuning it is the way Stanford Alpaca has been done, where the first stage is supervised fine tuning, followed by the instruction following examples that one is that we have generated. So this is the Forge LLM that is the open foundation model for science that has been developed here in our group. The downstream problems that we are working here are scientific question answering on scientific articles on each specific domain, the domain as I mentioned, astrophysics and material science. Information distillation, research article long form summarization is a form of information distillation, and the long shot hypothesis generation from previous literature. Astrolama is one of our foundation models that we have developed in collaboration with NASA and Astrophysics Smithsonian and Harvard University and the Australian National University. So this is the foundation model, the first foundation model of astronomy. In relation to this, I would like to mention about ChemPro, where this is from Andrew White's group in Rochester, where they are augmenting large language models with chemistry tools to accelerate knowledge discovery in chemistry. This is a very, very interesting paper where they have designed various tools where the background LLM is obviously GPT-4, but they develop various tools for thought, action, action input and observation. So I will, like, if anyone is there from chemistry background, they are very much welcome to, you can look into this. They are also a collaborator with ORNL, and yeah. Hypothesis generation, this is the base for that we have based our work, and we are currently collaborating with Allen AI, especially Tom Hope, with whom we are working here, where the idea is to use contextual literature-based discovery based on seed terms and previous literature. How do we automatically come up with new hypotheses given a problem statement? So this is still in a very, very nascent stage because hypothesis generation so far in different domains has been attempted at a very granular level, but we thought here that granular level might not always work because you need context to understand the science. So hence, mining the context from the research articles, previous literature for a given seed term, and then building on top of it and letting the downstream LLM to suggest a hypothesis is an interesting way to explore hypothesis generation. Novel materials discovery was a landmark paper from the Sealer Group in Lawrence Berkeley National Lab and University of California, Berkeley, Professor Gerber Sealer, who did a project where they mined tons of material science literature in order to predict future materials, and then they prove their hypothesis by freezing their language, their model up to a certain year, and then predicting the future materials in subsequent years. So this work was published in Nature, and you are very much welcome to go through this because this was a landmark paper which actually brought NLP into the mainstream material science community. Some very interesting work from Allen Institute is the Olmo, which has been, I think, 3 days back. It was 2 days back. It was released. The Olmo open source large language model which is truly open source, because if you talk about other models like Llama and others, only the weights are released, right? But not the checkpoints and others. So you can't do much. You can't click on Llama, right? Or you can't click on Vicuna or other similar models. But then Allen Institute has released everything that they have used. So almost 7 billion, 1 billion model has been released, and probably in the subsequent weeks they will release the 70 billion parameter Olmo model, which will be very interesting to see, and how that open source model compare with the closed source models like GPT or Anthropic or Claude. So Olmo has been trained on the 3 trillion token corpus that they have named as Stolma. You are welcome to look or follow their advancement. Yeah, so I want to talk about the regular workshops and the various challenges shared that we regularly organize with Smithsonian NASA under the ACL umbrella, and we have various tasks focused on scientific discovery. We also organize a scholarly document posting workshop series at RCL conferences, and this time is going to be happening with ACL 2024 at Bangkok this year. So you are very much welcome to be a part of this. Some shared tasks that some AI for science tasks, like for example, function of citation in astronomical literature, like we talked about citation classification, in-depth classification. So how do we classify various kinds of citations in that literature? That is something very interesting to us, and we propose the task, we develop the data set, and we invited the community to take part in it, and the participants finally evaluated, came out with a new evaluation metric for that, and then released the findings. So how do we take the C of scholarly knowledge? I would say it would be better thematic search, doing better query focused retrieval, doing better recommendation. It could be more content collaborative hybrid, be better question answering within the paper, or assimilating knowledge from external sources. Obviously distilling scientific information, because we can't consume the entire scientific knowledge, and obviously citing analysis to identify the important papers or important artifacts in science. So some of the AI for science efforts at ORNL that we are currently pursuing is scientific novelty detection, continual, how do we identify a new knowledge, new scientific knowledge based on the previous literature, right? And feel free to get in touch with me if you want to know more about this ongoing project. There is continual training of LLMs for downstream applications, which includes scientific question answering, developing models like Astrolama, Astrometral, MaxWi-Fi, in collaboration with these entities, fine-tuning various models, comparing their performance. Quartz, which is our in-house scientific language model. We are now converting Quartz into HPC chat, where we will be able to do HPC-related question answering. Our HPC-related knowledge discovery from much. Literature-based discovery efforts like hypothesis generation validation in collaboration with Allen Institute for AI, bibliography, data curation, and information extraction in collaboration with NASA. So these are, in short, the various kinds of efforts that are ongoing. Obviously, each has various sub-problems and multiple teams working on it. I'll be happy to discuss more on them if you want to know. But you are very much welcome to read the papers that came out from this various things. This is just a slide for people who are new to NLP. If you want to know more about the cutting edge research that is happening in the NLP domain, you should follow the ACL web and ACL anthology. Please follow the premier venues like ACL University, NACL, or others, some journals like CAC, ACL, NLE, or CSL, but only under the ACL umbrella because we know that there are a lot of garbage happening in the name of NLP. So it's better that we restrict our literature search or knowledge discovery from premier venues in order to elicit the latest scientific advancement. For example, BERT, GPT, and all these papers where BERT was actually an echo paper, and then what to get was actually a paper in Murex probably. And also GPT probably was released in Murex. So it's good to read paper from this premier venues in order to understand the current state of the art. If you're getting started with NLP, these are some links I would say that would help you to get started. At least for any PhD in AI, for example, the NLP textbook by Deepanjan, there's the LLM primer from Matthew Hannibal, wonderful, very much like many code examples. If you're new to deep learning, you can use this interactive book, the dive deep into deep learning from Zachary Lipton and the Text Analysis in Python is a very interesting book from my friend Kobe from University of Bocconi. Prompt engineering, if you probably that with the advent of large language models, there is a new way of interacting with models we call as prompt engineering. So in order to understand more about prompt engineering, RAG and things, to follow this particular blog by Elvis from Meta. Probably we will talk with Meta. AI. The Open AI Cookbook is really a very, very wonderful research for to explore GPT and alignment, super alignment kind of thing. To know about the latest things that people are doing with the GPT API or building on top of it. Yeah. Thank you. I think I rushed it too much, but I think we have now enough time to do some of the questions. What are the questions in the chat?
Sir, someone has written something in the chat box. Please read it.
Yeah, I'm trying to find. Yeah, okay, I found it. 6 months ahead of GPT-4 launch, Nilay Bhattacharya has written, 6 months ahead of GPT-4 launch, Michael Spencer wrote and their social media. How does the lay user decide which AI is best for which purpose? Okay. And then question 2 is how to manage the ethical issue of mobile PC, hardware association, and or adequacy. Okay, so regarding your first comment, Mr. Bhattacharya, yes, if you can recall, ChatGPT was launched probably, or GPT 3.5, where from the generative AI explosion began in November 2022. I was working in MySpace then, and we were also aware. In fact, Silicon Valley was aware that some big thing is going to happen, uh, or someone is going to do something radical um, in the AI space, and hence, if you see the timeline of our MySpace Copilot launch, it almost coincides with GPT because we were also working on similar kind of things, but on the but for scientific knowledge. So it's not only them; it's probably many of the people or investors in Silicon Valley. They were aware of the generative AI revolution way back because many of them were given early access to the GPT model much before their launch because they did a alpha and beta version. How does lay user decide which app is best for which purpose? I think it's a tricky question to answer, but I think there are many forums. I if you don't recall, I think one Crunchbase or something where if a new AI app is launched or they rate uh, the that particular app under various parameters, and those are done not by layman users but by expert users. And based on that, they also give ranking. For example, if you recall, in the last OpenAI general meeting when Sam Altman released the GPT store, when Sam Altman talked about the GPT store, and then GPT store was probably came into action 1 month back, there were certain apps which rank at the top. So, uh, it's really a matter of usage. It's really a matter of how how people are using it, the reviews, but also the very core technical expert users who are using them and then ranking them based on various parameters like interface, responsiveness, and stuff like that. Are you talking about any specific app you can post of the chat? Like specific app as if for some specific domain? Okay. How to manage the ubiquitous issue of mobile for energy? So uh, are you talking about the hardware appropriateness in terms of mobile and PC for this generative AI model? Yeah. So this has been a problem. This has been a problem in the sense that these models are very big, right? So absolutely on a consumer hardware like a PC or a mobile, it's not possible to run the bigger models. But then we are seeing that there has been an explicit push by the big tech to develop LLM assistants where you can have a LLM on chip or LLM on device, or even if you talk about the smaller models, for example the Llama 7 billion parameter model uh, or the Mistral 7 billion parameter model, there has been instances that people have told that they have run on their personal MacBook, but then those MacBooks are also equipped with several GPUs, one GPU card, right? So at the current moment where these models are so much data hungry, just imagine each model is taking 3 trillion tokens to get trained. So absolutely, without a large hardware pre-training or using those models, still is a distant ball game. But we are seeing increasing effectiveness. Today, I was reading a paper called the DSCA, uh, where it's a small, I think, 7 billion parameter model still like I mean, I'm telling it small, but it's still large. But in comparison to GPT, which is 175 billion, probably GPT-4 is a mixture of expert model, which is called failure parameter, right? So, in light of that, I would say DeepSeek math, the 7 billion parameter model perform better, or many a times they have shown equivalently or perform better than GPT. So as time progresses, not in this year, but maybe in the next year, we would see that we are achieving the same category of performance of large language models with small language models. So there has been already a push. For example, if you talk about the five, the paper I know the paper is called textbook is all you need, where Microsoft developed a five category of models, which we are also currently working on to train models on astrophysics book, not papers, and see how do they perform in comparison with knowledge discovery papers. So yes, there has been a push, but I think at this moment the push is more towards how to make generative AI more knowledgeable, or more knowledgeable in terms of doing reasoning, doing step by step, not thinking. I won't say thinking, but at least step by step or multi-hop reasoning over complex scientific problems. But yes, there has been a push, and probably in the next year we will see smaller language models uh, doing equivalent or nearly equivalent to the large language model. This year probably would be the year of large language vision model, where you see vision and vision community, VPR community, and NLP community coming together to develop models like Lava, which is also there, and then the university group is developing something called Astrolava, which because in certain disciplines like astronomy or material science, biology, specific between images are so critical. So without those, there is no point of developing science function models. So large language vision models we would see a very high research output this year. Mhm. Feel free to ask questions related to the presentation or anything else. Uh, yeah, I would be happy to answer. You can also unmute and ask if you want to. The pace at which the research in LLM is going is is really scary. It's very hard to keep track of the research, and that's why research assistance in terms of doing research is very critical. And AI is significant, so that we can consume more and more science quickly. Anyone among the audience are using ChatGPT in their research?
If anyone have any question, they can surely ask. Thank you, sir, for this mesmerizing session. We are glad to have you with us.
Thank you. So, Deepanjan, what should we do? Like, if there are no more questions, um, yeah, the participants can directly reach me if they would want to with their question. Yeah, you are on mute, Deepanjan. Deepanjan, I can't hear you. You are on mute.
Sorry. It's already 1:20 midnight, so we can conclude the session. And thank you, sir.
Okay, okay, no problem. Sure. Thank you. Thank you,
Thank you,
everyone.
sir.
Okay, bye.
Bye, sir.